Imagine a region in space where gravity is so strong, nothing can escape its grasp, not even light. This is a place where the rules of physics as we know them seem to bend and twist in unimaginable ways. This, my friends, is a black hole, a cosmic enigma that has fascinated scientists and stargazers alike for decades. It's not a hole in the traditional sense, but an immense amount of matter squeezed into an impossibly small space. Imagine compressing a star several times larger than our sun into a sphere no bigger than a city. Its density warps the fabric of space-time, creating a deep well from which escape is impossible once you've crossed the event horizon. This warping effect is so intense that it can bend light around it, creating a phenomenon known as gravitational lensing. Think of it as the point of no return. The event horizon is the boundary beyond which nothing can escape the black hole's pull. If you were an astronaut venturing too close, once you crossed the event horizon, there would be no turning back. You would be inexorably drawn towards the black hole's center. The black hole's gravity would inevitably pull you in, stretching you into a long, thin shape in a process scientists call spaghettification. The event horizon isn't a physical surface, it's simply the threshold beyond which the escape velocity exceeds the speed of light. It's an invisible boundary that marks the limits of our observable universe. What happens to things that fall into a black hole? Do they get destroyed or do they end up somewhere else? The details are still a subject of intense scientific research and debate. Some theories suggest they could be transported to another part of the universe or even to another universe entirely. From an outside perspective, an object falling towards a black hole would appear to slow down as it approaches the event horizon, its light becoming redder and dimmer. This is due to the extreme gravitational forces at play. This is due to gravitational time dilation. Time itself seems to stretch and slow down near a black hole. The singularity is the heart of the black hole, a point of theoretically infinite density where our current laws of physics break down. It's a mystery that continues to challenge our understanding of the universe. The journey to becoming a black hole begins with a colossal star, one of the true giants of the cosmos. We're talking about stars at least 20 to 30 times more massive than our sun, sometimes even more. These giants burn through their nuclear fuel at an astonishing rate, far quicker than smaller stars like our sun. For millions of years they shine brilliantly, balancing the forces of nuclear fusion and gravity in a delicate dance. Eventually, the star exhausts its nuclear fuel, having burned through it at a prodigious rate. The fusion reactions in its core cease, and the star's core collapses catastrophically under its own immense weight. The outer layers crash down onto the imploding core, rebounding in a spectacular explosion known as a supernova, lighting up the cosmos. A supernova is one of the most energetic events in the universe, blasting vast quantities of gas and heavy elements into space, enriching the cosmos. If the original star was massive enough, the remnant core left behind will continue to collapse, defying the forces that try to stop it. The core, containing several times the mass of our sun, gets squeezed into an ever smaller volume, becoming incredibly dense. Its density becomes unimaginable and gravity intensifies beyond comprehension, pulling everything inward. Eventually it collapses past a critical point, shrinking down to an infinitely small point called a singularity, and a black hole is born, a true marvel of the universe. The event horizon forms around this singularity, marking the boundary of this new cosmic enigma, beyond which nothing can escape. Could our sun collapse and become a black hole? It's a fascinating question that often sparks curiosity. The short answer is no. Our sun simply doesn't have the necessary mass to undergo such a dramatic transformation. Our sun is a cosmic lightweight compared to the stellar giants that end their lives as black holes. These massive stars are the true titans of the cosmos. To form a black hole, a star needs to be at least 20 times the mass of our sun. Only then can it collapse under its own gravity to such an extreme degree. Our sun is a G-type main sequence star, currently in the prime of its life, steadily fusing hydrogen into helium. This process has been going on for about 4.6 billion years. When our sun runs out of hydrogen fuel, it won't go supernova. Instead, it will undergo a more serene transformation. Instead, it will expand into a red giant, likely engulfing Mercury, Venus, and possibly Earth. This phase will mark the beginning of the end for our sun. After the red giant phase, the sun will shed its outer layers, creating a planetary nebula. This beautiful glowing shell of ionized gas will be a sight to behold. What remains of the sun's core will be a white dwarf, about the size of Earth, but containing roughly half the sun's original mass. This dense remnant will be incredibly hot initially. It will slowly cool down and fade over billions of years, eventually becoming a cold, dark black dwarf. This final stage will take an unimaginably long time to reach. So, while our sun will eventually die, its demise will be a relatively gentle fading away, not a cataclysmic collapse into infinite density. This slow fade will be a quiet end to a long stellar journey. Our solar system will look very different, but it won't be home to a black hole of solar origin. Instead, it will be a testament to the life cycle of a star like our sun. Imagine, through some impossible magic, our sun instantly collapsed into a black hole. What would that mean for us in the solar system? Would we be instantly sucked into a vortex of doom? The crucial thing to remember is that the sun's mass hasn't changed. It's still one solar mass, just compressed into an incredibly tiny volume. Gravity depends on mass and distance. If the sun's mass remains the same and Earth's distance from the sun's center of mass remains the same, the gravitational pull Earth experiences would also remain the same. Earth wouldn't suddenly be sucked in with greater force. It would continue to orbit this new, tiny sun-mass black hole in the same elliptical path it follows today. The same would be true for all the other planets, moons, asteroids, and comets in our solar system. Their orbits are dictated by the sun's mass, not by its size or what it's made of. The immediate danger isn't being pulled in, but the absence of sunlight and solar warmth. Earth is now orbiting a black hole that possesses the exact same mass as our sun. Our planet's orbit remains stable. We wouldn't suddenly spiral inwards towards oblivion. The gravitational force between two objects is proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. Since the sun's mass, now a black hole's mass, hasn't changed, and Earth's distance hasn't changed, the force remains the same. The tides, governed by the gravitational pull of the moon and the sun, would continue much as they do now. The length of our year would remain unchanged. The real problems would arise from the absence of sunlight and solar warmth. The most immediate and catastrophic consequence of our sun becoming a black hole would be the sudden and complete absence of light and heat. Darkness would fall upon the Earth. The stars would blaze with an unfamiliar clarity in a sky devoid of the sun's glow. Without the sun's energy, Earth's surface temperature would plummet rapidly. Photosynthesis would cease almost immediately, leading to the death of most plant life within days or weeks. As plants die, the entire food chain would collapse. The oceans would cool more slowly than the land, but eventually, they too would freeze over. Within a few days, the average global surface temperature would drop below freezing. Within weeks, it would be tens of degrees below 0 Celsius. Life as we know it would be extinguished. Earth would become a rogue, frozen world, orbiting its tiny, dark master, the solar mass black hole that was once our life-giving sun. The fate of Earth would be mirrored by the other planets in our solar system. Mercury and Venus would become even colder. Mars would plunge into a deeper freeze. The gas giants would feel the chill, though their internal heat sources would keep their deeper atmospheres somewhat warmer. Their many moons would lose the faint sunlight that illuminates them. The entire solar system would transform into a collection of dark, icy bodies, silently pirouetting around an invisible central point mass. The orbits themselves would remain stable for billions of years. The solar mass black hole would exert the same gravitational influence as the sun did. The Schwarzschild radius defines the size of the event horizon for a non-rotating, uncharged black hole. For any object of a given mass, if you could compress all that mass into a sphere smaller than its Schwarzschild radius, it would become a black hole. The formula to calculate the Schwarzschild radius, Rs, is Rs equals 2gm over c squared. For our sun, the Schwarzschild radius is approximately 2.95 kilometers. This means if you could somehow crush our entire sun down into a sphere less than 6 kilometers across, it would become a black hole. That's an almost inconceivable level of compression. Imagine squeezing something the size of a star down to the size of a small town. This tiny size is why, even if the sun did become a black hole, Earth wouldn't be immediately sucked in unless it got very, very close. At our orbital distance of 150 million kilometers, we are vastly far away from this critical boundary. The most important takeaway is that our sun will not and cannot become a black hole. It simply lacks the required mass. Stars need to be born with many times the sun's mass to end their lives in the kind of core collapse that forges a black hole. Our sun is destined for a more sedate end as a red giant, then a planetary nebula, and finally, a cooling white dwarf. If the sun were to instantly transform into a black hole of the same mass, the Earth and other planets would continue in their current orbits. However, the cessation of sunlight and heat would be catastrophic. Earth would rapidly freeze, and life as we know it would perish. This thought experiment teaches us valuable lessons about gravity, stellar evolution, and the delicate conditions necessary for life. While our sun won't become a black hole, studying these exotic objects deepens our comprehension of gravity, space-time, and the ultimate fate of matter. The cosmos is full of wonders, and black holes are certainly among its most fascinating and mind-bending creations.